morning. Hello, everybody. I'm Brian Bassett. As Nick said, thank you. Welcome to the 2023 Data Summit. We're happy to have you here. I'm the chair of the event, and I work at a business in town called Simple Thread, director of business development there. Just to say, these events are a long time in planning and coming together. This event started many, many years ago. We had one event right before COVID where it felt borderline irresponsible to have it, and then we have been building back on that program. But it's great to be in the second year back into the location that we were at prior to COVID. So welcome, everybody. So glad you're here today. Today's event, this Data Summit would not be possible without two main groups, which I want to make sure that we recognize. The first are the sponsors. They should be up on the screen behind me here. You'll see Altria, CoStar, UDIG, VCU, Vaco, Carmack, Confluent, CDW, and VCU. So let's give them a round of applause, please. Thank you so much to our sponsors. We could not do this event without you, so thank you. Also, the committee that helped me plan this event, they were instrumental in this. I did data engineering work far too long ago to remember or know what's relevant these days, so I rely on the committee to help us understand what topics we want to hear about every day, in this conference, and what's relevant today. What do practitioners need? What do leaders and managers of teams need in kind of this modern 2023 era? So they are really invaluable in getting to that. So if you are a member of the committee and you're in this room, please stand up. I want to make sure that we recognize you. So please stand up, folks. Yeah. So thank you to some of our committee members who are here. Thanks, guys. Basically, just want to say that as we move forward, we're going to hear from an amazing speakers today. Our first is Keegan Hines. He is looking at my notes. He just changed jobs this week, so he is a principal of applied science, a principal applied scientist at Microsoft. He's also an adjunct professor at Georgetown University. Previously, he was the director of machine learning at Capital One and is the co-founder of the Conference on Applied Learning for Information Security, CAMLIS. Keegan studied physics at Washington and Lee. He earned his PhD in computational neuroscience at the University of Texas. Please, let's give a warm welcome to Richmond's own Keegan Hines.
All right, awesome. Well, thank you very much, Brian, and the organizing committee for inviting me here this week. I really appreciate the invitation. I really miss events like this, and I think I've gone to a conference since 2019 in person, and so I think we all really miss kind of getting together and talking about what's going on, and that's cool. And so I'm really excited to be here, and when Brian asked me to come give a talk and what would I be interested in speaking on, the first thing that came to my mind was generative AI. I told you, have to talk about this. It's all that anybody wants to talk about. And so today we're going to be, speaking about generative AI, and my cute little subtitle here, wow, that escalated quickly. That sums up how I feel about it. I kind of wanted to sit down for myself and figure out what in the world just happened. How did we get here? And so that's what I'm going to present back to you today and kind of take us on a walk through what just happened in the last probably 8 years, but really just in the last 18 months, where things got especially weird. And so a little bit about me, I'm 2 days into a new job at Microsoft. So prior to that, I was head of machine learning at a startup called AI, focused on monitoring and managing machine learning systems. Before that, I worked at Capital One, leading machine learning research group, and as I mentioned, I also teach as well. A long time ago, I actually used to work here at the Science Museum of Virginia. When I was in high school, I volunteered here teaching kids about physics. So it's kind of fun to be back here. So let me start with where are we, what's going on, and then we're going to kind of take a step back through history. So as of about 6 months ago, we now live in a world where I can do things like this. I can effortlessly create new images according to text prompts. So if you look at the figure on the top left, It says a golden retriever wearing a blue check beret and a dotted turtleneck. It's a natural language text prompt, and I can generate a fully realistic, high-res image of exactly that thing at the bottom you see here. So this is an example of an image generation model from Google, like Imagen, and this was completely impossible 5 years ago, especially the level of control you're seeing here with a natural language text prompt. This is brand new. And then, of course, in generative text, we're seeing similar things. Surely we've all played with ChatGPT at this point. GPT-4 was just publicly announced a couple weeks ago. It can do a lot of very wild things that we'll talk about. Not only can it generate, long sequences of very realistic text. For example, you can say, write me a Shakespearean play about a llama and an astronaut, and we do that, and it makes a lot of sense, and it's syntactically perfect. But beyond that, it can have this ability to reason and understand. So if you look at this example here, the input prompt is it's kind of a riddle. So it says, well, imagine you have a book, 9 eggs, a laptop, a bottle, and a nail. Please tell me how to stack them onto each other in a stable manner. And if you look at the response, it's quite eerie, to be honest. So it's okay, well, let's place the book flat on the level surface. We're going to arrange 9 eggs in a stable square. We're going to put the laptop on top of that, and so on and so on. So not only is this a valid bit of text and sequence of paragraphs, but it actually seems to imply that this model has an understanding of the physical world to answer this riddle, right? It has a notion of concepts like books and eggs and how an egg and a bottle could be related with respect to gravity. That is a major change, and we'll kind of walk through how we got there. So what we're going to talk about today is mostly a historical tour. We're going to spend most of our time talking about generative text models. For the sake of time, I'm going to leave out the generative vision story, and we'll visit it a little bit. But I'm going to focus mostly on generative text. I think that's the most fun, and I have a feeling that's what we've all been playing with a little bit in terms of ChatGPT. So I want to make sure we get there. Then we'll check in on what do we have today, what companies are emerging, what products are emerging that are taking advantage of all of this. And then a little bit of a glimpse of where are things headed. What are some of the challenges that we're going to face in this area going forward? So let's talk about generative text. These are some of the major highlights. Obviously, there are many thousands of research papers that have occurred over the last bunch of years that have gotten us to this moment. I'm going to hit kind of the major highlights. And because we're a broad audience, I'm not going to dwell too much on the technical how things work, and instead we're going to talk about sort of what these things are aspiring to do. Some of the major players here are going to be recurrent neural networks, attention, transformers, GPTs, things you've heard of like ChatGPT and so on. So let's start at the beginning. Let's forget about deep learning for a moment. And let's just talk about the idea of how could we generate realistic text if we wanted to. What we're going to need is something called a language model. Now, a language model can be implemented in lots of different ways, but in general, the idea is I want some kind of flexible mathematical toy that's going to allow me to learn patterns from data. In particular, I'm going to learn patterns from text data, like books or the whole internet. I'm going to learn the sequences and the correlations and the co-occurrences between letters and words and things like that using a language model. Now, just to make things concrete, we're going to start with a very specific and simple language model and kind of work through a concrete example. What we're going to look at is what's called a first-order Markov model. Now, this is very, very simple and frankly kind of boring, but it turns out to work surprisingly well. And what a Markov model is it's just a way of memorizing the probabilities between two things happening. So if I have the letter B, what's the chance that I'm going to see the letter A next? If I have the letter Q, what letter is going to come next? It's going to be a U, right? That's a very high correlation in English, and so on. And so when we're thinking about a language model, this is a choice we can make. So let's stick with this simple one, and let's imagine that we're going to have a Markov model over correlations between characters. So there are 26 characters in English, and I just want to count up, given that I have any particular letter, what's the probability of the next letter. So this entire Markov model can be characterized by what's called a transition probability matrix. And so that's what I'm showing over here on the right of the slide. It's just a big table of numbers where I've gone through a whole bunch of text and I've counted up all those things. So I've gone through maybe all of Shakespearean English, or I've gone through a whole dictionary, or I've gone through any pile of words, and I've just counted up all. Every time I saw an A, what's the probability I followed immediately by another A? Well, that transition is actually pretty rare. The word aardvark is the only one I can think of. So that's got a pretty low number. But if I saw an A, what's the probability that I saw a B? Well, that's more common. There's a lot of words that go like that, and so on. And so you just imagine filling out this big 26 by 26 table with these numbers, right? So it's just counting and then kind of turning those into probabilities. So why is this useful for generating new text or new language? Well, now I can just use this as a starting point, and I just take kind of a random walk around this table. So let's say, for example, I start with a C letter, like the letter B. So look at this column, this B column here. And given that I started with a B, I say, well, what's a high probability next letter? Well, maybe it's an A. So I'll pick that. And so now I have a sequence with B, and then A, and then I ask, given that I have an A, what's another highly likely letter? So we go over to the A column, I look down, and I say, I don't know, maybe B is pretty highly probable. So I have B, and then A, and then B, and I just generated a valid English word, the word bad. So this is a generative model of language. It's a very simple one because it's only taking into account one-to-one correlations, or pairwise correlations between tokens, and here the tokens are letters. These are all tokens that we can change and will change as we make more complicated language models. And if you think about the tokens, the vocabulary, the length and duration of correlations that we want, this is where things have really gotten more and more expansive with larger deep learning models over the years. So that Markov model is a thing to keep in mind. And as we go through other kinds of mechanisms, just keep in mind that it's going to be a similar premise, but what we want to do is we want to expand to longer-term correlations in sequences. So it's not just going to be, one letter to one letter. It's going to be 5 letters to 5 letters, 50 letters to 50 letters, or it's going to be words, or it's going to be phrases, and looking at long-term correlations. And so let's go into deep learning now. So let's imagine that we have some familiarity with deep learning. There's an idea called an artificial neural network. Again, this is just a flexible mathematical toy for learning relationships between inputs and outputs. And there's a particular flavor of this called a recurrent neural network that we can apply to sequences. So again, I'm going to look at an input sequence, and I'm going to use this artificial neural network, and I'm going to over and over and over again kind of recalculate correlations that go along those sequences. There's a lot of flavors of this that you may or may not have heard of. LSTM, GRU. You don't need to worry about it, but just know that there is a mechanism here in deep learning for capturing longer-range correlations than our simple, tables could capture. This turns out to work surprisingly well, and there's many things in deep learning. This is actually a pretty old idea that came out in the 80s, and it wasn't until around 2012, 2013 that the computational capability caught up, and this stuff started to work really well. So there's a nice blog post here where the author used one of these LSTMs. He trained it on the entire source code of the Linux operating system, and then he generated new code, character by character, similar to what we just did, using that LSTM. And he has what you see on the right, which is a valid C program. Right? So this is code that actually compiles, it runs, it does something. And so in the course of that, by just kind of looking at character-to-character transitions, this deep learning model is able to understand what things are highly likely and what things are highly unlikely. And as you can see, the code is syntactically correct. It learns even like white spacing and things like that, moving on from there. And so RNNs and LSTMs were a big improvement to allow us to learn correlations, longer correlations in sequences. And so that's going to be the name of the game as we go forward. How can we get longer and longer temporal correlations to get a really good language model to understand kind of the nature of these things? So the next major innovation here came around 2015 with an idea called attention that you might have heard about. So attention was first introduced in the context of one particular task called machine translation. Machine translation is the task of, let's say I have a sentence in English and I want to translate it to French, and I want an algorithm that can do it for me. Early advances in machine translation came about using LSTM. And in fact, there were very successful early demonstrations that you can use an LSTM that takes in a sentence in English, the RNN would kind of process that sentence, and then it would output a new sentence in French, and it worked really well. What's really fascinating about that is that a model like that doesn't know anything about English grammar and syntax. It doesn't know anything about French grammar and syntax. Again, it's just studying patterns in data and can be really effective at doing that. The limitations of those models at the time was that you could do a really good job with short sentences, but if you had longer sentences or paragraphs, things started to be not so good in translation. And so again, the bottleneck here is, can we understand and process longer and longer sequences? If I have 50 words long, 100 words long, how can I have a deep learning model that can handle that and do really well? And the challenge is that in that machine translation, you're taking the whole English input sequence, you're collapsing it into what's called an embedding using that RNN, and then you're using that to generate the French output. That's a really challenging thing to do because that representation has to capture all the complexity. You're kind of taking a really complicated sequence and you're kind of compressing it. And that compression has to work really well. And it has limitations on how well it could work. And so in 2015, we saw several concurrent papers that introduced an idea called attention, which says, well, now we're going to change the translation process a little bit, such that when I'm doing the output translation, as I'm outputting French words, one at a time, I get to look at the input sequence again and again. So I get to look at the whole English sequence again and again instead of just one time. Now, if you look at it in exactly the same way again and again, there's no new information. That actually didn't change the computation. But instead, the idea was, well, maybe I can give different weighting to different words in the input sequence each time I glimpse at it. And that weighting was sort of anthropomorphized with the word attention. So it's as if I'm translating the third word in the French output, I'm going to attend mostly to probably the third or fourth word in the English input. Right? That's probably the most relevant stuff to look at. And so as you're going through the output sequence, you kind of change where you're paying attention as you go along. You can visualize these attention weights with the kind of heat map you see in the middle of this slide. So on the left side, you see the French sequence, on the top you see the English sequence, and then the color in the heat map is telling you how much attention weight is going into aligning these two things during the translation process. You see a lot of color on the diagonal because mostly the words in English and the words in French are one-for-one, right? So in doing the translation, it kind of makes sense to pay attention to the corresponding words. However, there is a phrase in the middle of the sentence, which in English is European Economic Area, which in French, the noun and adjective are kind of swapped in the order there. So you can see that there's kind of a break, and the attention kind of needs to pay attention to 3 or 4 words at the same time to get that translated correctly. So this is the idea of attention, and it's just a different way to add a new mechanism to the current neural network that expand their ability to learn long-range sequences and long-range correlations. It was really an important breakthrough at the time, and in fact it was only 2 years later that we got to the figure on the right. So in 2017, there was a paper from Google called Attention is All You Need. And what they were pointing out is that this idea of attention and a variant of it called self-attention is in fact so useful and so powerful that it's all you need. So the recurrent neural network actually serves no purpose anymore, and all we need to do now is think about this attention idea. So between input and output sequences, and if I kind of have this mechanism where I can look at things and spread my attention in multiple ways, that's all we're ever going to need again. And so it was in this paper that they introduced a new kind of deep learning module called the transformer. A diagram of that is shown on the right. I'm not going to dive into how it actually works, but the idea is we're going to use this self-attention mechanism with multiple flavors of attention that all kind of come in, and we're going to stack these on top of each other. So we have this deep attention, deep learning model called the transformer. And this really changed things. This is really a spark that really changed how processing of sequences was done from then on out. And at this point, I'll mention that, again, the task here was machine translation. That is a generative task, right? We're trying to generate English or French from an input and things like that. But it can also be applied to many, many NLP tasks. Document summarization, document classification, lots of different things. And part of it is generative. So shortly after this, we began to see kind of general purpose LLMs. So there was a model called BERT, which became very useful around the same, that was from Google, around the same time that a paper called Generative Pre-trained Transformers, GPT, which is now quite famous, came out. And they both had one thing in common, which is you're going to take one of these transformers, right, almost the identical thing that was published in this Google paper, you're going to make it a little bit bigger, and you're going to train it on a bunch of tasks simultaneously. So you want to make it really good at doing a lot of different NLP benchmark tasks at the same time. And also, part of the training, and this is the G in GPT, is that it's generative. So we're going to have this model kind of take in some bit of text, generate what it thinks the next text is. So it's going to kind of auto-complete itself, and then check how well did I do. And so the training objective is sort of, as I'm generating new text, how much does it match the actual text? And so this is
the generative pre-training, where it's, again, just trying to kind of learn the reasonable statistical patterns of text and be able to recapitulate them. This was a really interesting moment for NLP, where now this BERT especially became kind of the standard for transfer learning in NLP, which had been lagging behind computer vision. In the computer vision field, there had been these large, convolutional neural networks that somebody would spend millions of dollars to train, and then you could kind of download it and tweak it for your own problem, and it would save you millions of dollars. That process is called transfer learning. This was the first moment in NLP where that same thing could be done, and that's even true today. You can just download a package called Hugging Face. You can download BERT, any of its cousins, and you can make instant use of all the effort that went into training that thing. So here we are at transformers. We're at these general purpose transformers. Again, these are deep learning models that are designed to process sequences and do really well with sequences. And I'm going to pause the story right here, or kind of talk about a new thread that I call OpenAI's big hypothesis. So around this time, OpenAI starts publishing a lot of blog posts and papers on what they call scaling laws. And if you take a look at this diagram, this is showing what's called a training curve. So on the x-axis we have sort of the amount of data that a model has seen in its training process, and on the y-axis we have how good is that model doing. It's something called the test loss. So lower is better. You want less test loss. And there's a few things to notice from this figure. First, take a look at the purple curve. One of the things they're looking at is, I'm going to do this GPT paradigm, and I have a lot of choices about how big the model is, how deep it is, how many parameters it has. I have a lot of choices about how much data goes into this thing, and they're just going to explore the space, right, the design space of these transformers, and see what they can figure out in terms of patterns. So let's take a look at the purple line, which corresponds to a small model, 10 to the third number of parameters. And we see it has a loss curve, right? It learns, and then it bottoms out. That's pretty common, right? You kind of get the most signal you can. So if you compare the small model, 10 to the third, to the big model, 10 to the ninth parameters, again, that's the purple curve compared to, let's say, the green or yellow curve, you see two things. One, obviously, the bigger model does better on the total final test loss, right? The bigger model can become a better model in any of these tasks, any of this test loss. Maybe that's not so surprising. But the other interesting thing is the bigger model actually becomes better faster with less data than the smaller model. So if you look at the purple curve relative to the yellow curve, even at any given kind of level of test loss, like 8 or 6, it actually took less data to get the giant model to that level of test loss than it did to get the smaller model to that level of test loss. And so for the kind of the practitioners in the room, this has kind of odd and counterintuitive implications about age-old ideas in machine learning, like overfitting and generalization. These models up until now had been really good at just kind of memorizing the noise in data and not necessarily the signal. And so there's this whole thing about the avoidance of overfitting. And yet, we start to see a new narrative around, well, that's not really happening anymore with some of these models. In fact, the bigger the model is, the better things are looking, and there's really no reason not to do bigger and bigger and bigger. Here's the same kind of idea shown in a different way. So in each of these plots, we have kind of logarithmic in the x-axis in three different kinds of things. The amount of compute used, the amount of data that went in to train the model, the number of parameters in the model, like how big the model is. And then again, on the y-axis, we're seeing the test loss. So we're logarithmic in the x-axis, and what they're pointing out and what they're starting to call scaling laws is this observation that the more whatever you put into it, whether it's data or compute, the better the model gets. And by the way, there doesn't seem to be a bottom. So the scaling law meaning that it's conceivable that this process could go indefinitely. The bigger the model, the more data, it's just going to keep getting better. There's no reason to think that this is going to stop anytime soon. And so this, again, is what I call OpenAI's big hypothesis, because at this point, when they're talking about this, they go into a kind of a paradigm shift. And from the outside, it looked like all the various projects at OpenAI that weren't related to this somewhat paused, and everybody kind of jumped on this ship. And the idea was, how far can we push this? And around this time, they started saying that, like, let's keep pushing these graphs further and further and further with larger models and more data, because this is going to be the secret. And I'll point out that they weren't claiming, hey, this is just the secret to really good language models. They were, in fact, claiming this is the secret to true artificial intelligence, which is a strange claim, to be honest with you. And at the time, it made no sense. I didn't think it was going to work. Obviously, they're smarter at this than I am, but it did work. Because there's no reason to think that, better and better language models necessarily has anything to do with intelligence, necessarily anything to do with, a system that can reason, a system that can understand the world around it, right? It is believable that you could get a better and better language model, but there's no reason a priori to think that this is going to get us to true artificial intelligence. But that was their big bet. And, well, they were much more right than I was. And so they pushed this for a while. And then GPT-3 was a really big outcome here. And so this is the title of the GPT-3 paper. Notice that the title is not, GPT-3, this time it's 3 times better. The title is Language Models Are Few-Shot Learners. They titled the paper this because this is a surprising, emergent capability of a language model called GPT-3. The idea of few-shot learning is, so in machine learning, you typically train a model for a specific task with many, many examples, tens of thousands, hundreds of thousands of examples to do a supervised task, and they get really good at it. But we humans can do this thing that machine learning cannot, which is called few-shot learning, which is if you want to teach me a new game or a new task that I've never seen before, you probably only have to show me 2 or 3 examples, and then I'll get it. I'll figure out the pattern. Machine learning models can't do that, but that's called few-shot learning. And there had been some research in, how do we, this is an obvious gap in intelligence between our machine learning models and what humans can do. How can we kind of make progress in this few-shot learning? And frankly, there really hadn't been any progress. Until one day, it was discovered that these language models, in an emergent way, can do few-shot learning, can do, as we'll talk about, reasoning and things like that. Here's an example, might be a little hard to see, of what few-shot learning looks like in the context of this language model, but on the right, it's all about the prompt that you give to the language model if you're going to kind of teach it a new task or teach it a new game. So in this example, you're giving it an instruction prompt. Look at the far right. It says translate English to French, and it's got a couple examples of a valid translation, English to French, and then it says, okay, give me a new one you've never seen before. And there were many, many examples from the GPT-3 paper and then from people exploring after that. You could just invent new games like, here's a pattern, find this pattern, complete this sequence, do analogy games, things like this that the model was absolutely not trained on, but with a few examples in the prompt could pick up the pattern in the same way that a child would. Right, with just a few examples, you get this emergent capability. And so this is the strange thing, kind of going back to the big hypothesis. There's really no reason this should have happened, right? We're just learning about statistical properties, statistical correlations between words and letters, and yet this emergent, strange thing, has happened and has gotten us to where we are today. So the last chapter in this story in the last year was how do we incorporate human feedback into these things? And so there's a topic called reinforcement learning with human feedback, which is really in depth, and we could spend an hour talking about it. But it's about, well, these things can always spit out some output that's pretty reasonable. How do we make it more aligned to the things that we humans would find useful? And this RLHF thing is a way to change the way these models are trained so that you can incorporate human feedback and ranking. And so what ends up happening is the teams would turn to teams of humans who would look at, a number of, maybe you ask the model, you give it a prompt, it gives you 10 outputs. The humans would then go rank those 10 outputs, and then you get tens of thousands of examples of that, and that becomes your new training procedure, right? Kind of thinking about what are the things that the humans prefer. And so that was a really big change in not just are these things good at generating realistic text, but now they're good at generating helpful text, like frankly, really useful text. And so there was a model in a paper called Instruct GPT, and then that led into Chat GPT, which I think we've all played with at this point, which is a genuinely helpful chat agent that can converse with you in a very helpful way. if you see just one kind of before and after example here, so the prompt up on the top left is, here's a chunk of code. Tell me, what is the purpose of this code? On the bottom left, that's what GPT-3 would output, and on the right is what Instruct GPT would output. And so what GPT-3 would output is what looks like a multiple choice answer bank, which, if you think about it, is an interesting output, and we can kind of figure out why that makes sense. So at some point, ChatGPT thinks like, oh, maybe this is a question from a test, and a very valid next thing to predict would be a multiple choice answer bank, right? Remember, it's trying to autocomplete sequences. That's all it's trying to do. So that's probably a highly probable thing to output. But it's not a helpful thing if we're actually asking it for help. And so doing this RLHF thing gets us to the answer on the right, where this is actually a helpful, addressing the question that comes up, and the model is kind of interpreting, what goes on and describing to us the program. And so again, kind of the final step in that was ChatGPT, which we can all kind of tinker with and play with. And not only does it, produce valid, very interesting text, it has knowledge of the world, right? I asked it for travel plans, and it gave me a pretty decent, explanation of how to do something that I wouldn't quite know how to do, as we see an example there. So that's sort of a quick history of these generative text models. We're going to kind of take a look now at what's going on in products, startups, and the various models that are kind of in this family, and where things are headed next. So just checking in on the generative vision story, which we kind of skipped, but again, we live in a world now where I can say, generate me a hyper-realistic photo of a boy on a beach wearing a cowboy hat, and it's done, right? And it's a completely semantically valid picture. I think we're not too far from a world where you have kind of natural language Photoshop, where I could say, okay, here's an image, make his shirt blue, give him a toy in his hand, things like that, and you can kind of interact in that way as it's kind of generating synthetic new images. Here's GPT-4. There's not a lot that's known about how GPT-4 was trained, but one thing is that it's what's called multimodal. So it was trained on both text and image input at the same time. And what it can do, as it turns out, is visual reasoning. So if you look at this example, here's a photo of a fridge, the contents of a fridge, and the text prompt is, what are a couple of meals I can make with this? And you see the answers, well, you could make a yogurt parfait. You got strawberries and yogurt, or you could make a carrot and hummus wrap. This is wild to me. I guess for context, I point out that this task of here's an image, give me some recipes, that could have been a whole PhD, a year ago, right? And you could think about the different components that would go into that. You would need object detection, you would need this and that, you would need a knowledge graph about food. And as it turns out, GPT-4 can just do this on accident. And so there's a paper that came out 2 weeks ago called Sparks of Artificial General Intelligence, where a bunch of authors at Microsoft Research who had been playing with GPT-4 for about 6 months just enumerate 100 pages of different toys and demonstrations and examples. It's a very readable paper because it's just a bunch of trial and error. It's not very technical, of just these wild things that, again, nobody planned for it to be able to do this. Nobody would intentionally train a language model to do this. It just happens to be able to do visual reasoning. And so that's kind of the wild state that we're in right now. So there's a lot of companies, a lot of products that are coming out every day in this space. Obviously OpenAI and ChatGPT. Google kind of came to with their rebuttal with Bard. In the vision space, there's a company called Stability AI and Midjourney that you might have heard of. Adobe just released a product announcement about how you're going to integrate this stuff into Adobe. There's startups that are also meeting the challenge here with their own LLMs. There's a company called Cohere and Anthropic. These have tended to be spin-offs from Google and OpenAI, who are in the race as well of kind of having their own big LLMs. And we talked mostly about text. We talked a little bit about vision, but there's the interesting thing to me is that there's all these other modalities that we're going to start to see more of. So music, for example, there have been several generative music models that have either been talked about or put out publicly. There's one from Google called Music LM. There's one called Refusion. So you could say, write me a classical violin piece that sounds very moody, and you'll get a piece of music. And it's also impacting other areas of science. So I have an example here on molecular design and protein structure prediction. This is from David Baker's lab. He's at University of Washington, and he's an academic who wasn't very closely involved with AlphaFold. But the idea here is, can I use some of these things that were components that we kind of brushed over called diffusion models, and can I design molecules that have a certain structure, right? So can I say, well, give me this protein or give me this molecule so that it'll bind with that receptor, right? Imagine how quickly drug discovery is going to happen and drug development is going to change if we can just do the design of molecules that effortlessly. And of course, there's a lot of cool product coming out every day where we can leverage this. Axios HQ is a cool product that's spun out of Axios, where they do a lot of generative text so that you can summarize your own writings and documents inside your company, but in the style of an Axios journalist, which is kind of fun. Copilot from GitHub writes code with you. It's kind of your AI assistant for writing code. In the last couple of weeks, we've seen GitHub's parent company announce a lot of copilots to assist you, like with making presentations and making documents and things like that. So these AI assistants are going to be everywhere. I would not be surprised if a year from now you might see a feature in something like Google Slides where it's like, hey, generate me 10 slides on World War II, and it'll be done, right? And kind of help you get started there. There's a cool company called Jasper, which does content marketing. So it uses generative vision models and generative text models to create ad copy for you, really effortlessly. They're doing really well. People love their product. And many, many startups every day, right? As soon as I make this slide's going to be out of date. There's a fun blog post here called "The Landscape of Generative AI Landscapes," right? So every VC now is rushing to publish their eye chart slide of all the generative AI startups. This is just one. We're going to see this proliferate everywhere, especially with how easy it is to access things like ChatGPT and GPT-4 through APIs, how quick it's going to be to build new products on top of this stuff. So kind of looking back, I was trying to speculate on how this happened so quickly and why this stuff changed so quickly relative to kind of the history of computer science. And we can't deny that a big part of how this happened was open source software and an industry that was willing to share with each other. There weren't a lot of walls, there weren't a lot of moats. So all these industry and academic professionals were putting these models out, not just like publishing at the big conferences, but putting the model out there so that as soon as it's out there, a grad student could take it, tinker on it, and then a week later have a new idea about how to go next. This was all built on the foundation of really easy to use deep learning frameworks like PyTorch and TensorFlow. And so, a lot of work went into that so that you're not spending a lot of time on really hard, boring stuff, and you can actually think about new models and architectures. And then we have aggregators like Hugging Face, so that people who aren't the researchers designing these things, you can use Hugging Face and you can download these models and just play with them immediately, and get really a good handle on how things are going. And then there's also this openness, which I think ChatGPT did in a really unique way. So Stable Diffusion, one of these image models, it was released. It was a huge deal because they released the model and you could download it on Hugging Face. But you still have to know a thing or two about code to benefit from that, right? And you have to be comfortable doing that. ChatGPT did the opposite. They said, here's this crazy model that humans have never seen. We've never seen anything like it before, and all you need is a web browser, and you can interact with it. And I think that was a big part of lit the fire, not of the research, but of the frenzy and the excitement around this technology, is that my parents are playing with ChatGPT and asking me about it. And it's super exciting, and it's costing a ton of money, but surely it will be worth it for OpenAI in the long run financially. But they just made it effortless for people to engage with the science in a way that had never been done before. So what's next? There's a lot of challenges in this space. I'll talk about some technical challenges and then some social challenges. And the technical challenges with these LLMs, there's an issue that people are calling hallucinations, which is that an LLM, given any prompt, will always tell you something. It'll always give you like a nicely formatted language output, even if that is unsupported in reality. So to give you a fictitious example, you might ask, who was the first US female president? It'll give you an answer, even though that answer isn't rooted in reality. They tend not to do that anymore, but so how do you fix that? How do you tie its outputs and make sure they're supported in the reality that it's supposed to be tied back to. In the Instruct GPT paper, they noticed this problem, and they say that the RLHF process actually helps out a lot in kind of grounding these things in reality. And personally, I think this is actually quite a solvable problem, because once a thing generates an output, most of the time it's pretty easy to do verification. If it's outputting about specific entities or facts, and I have a knowledge base or a knowledge graph, I can pretty quickly check, right? It's much easier to check than to generate. So I actually think that the hallucinations problem is going to be pretty easy to solve. When there's issues of bias and toxicity, the generative chatbots have had a rough history of doing terrible things, and there have been a lot of blunders. And so the researchers in the field of AI alignment are trying to understand, how can we make systems like this align with the values that we hold dear and not say or do things that are against those values? So that's a great aspiration on the technical side. The RLHF is kind of how you accomplish that. It does beg the question of who gets to pick the values, and what do we think about political division and how all that's going to play out? Are we going to see an LLM for everyone's political preference? Unfortunately, maybe. But definitely tough things to think about. There are legal challenges too. So I mentioned GitHub Copilot, which is the thing that writes code for you. There's actually a class action lawsuit against GitHub for that, saying that the injured class is the set of all software engineers who put open source software into GitHub, because that was the training data, and that they were unjustly harmed because now GitHub is going to profit from that. And they're doing that wrong, and they're violating copyright law, and they're violating software licensing law and things like that. By having a generative model that was trained on everybody's data. Same thing with this Stable Diffusion, this Vision one. There's another class action suit from a bunch of artists who are saying that a model like that was trained on a bunch of copyrighted art, and that's unfair, right? That they're inappropriately profiting from the use of these artists. So this is really interesting in the legal landscape. I think there's going to be some really interesting stuff there. There's a Google case at the Supreme Court a couple weeks ago that wasn't involved in this, but Gorsuch was asking questions about algorithms that can generate their own content. So he's kind of anticipating where things are going. So I think it's going to be really interesting on the legal side in the next few years. And then there's social challenges. There's a lot of tough and sad stories about people falling in love with chatbots. It's not hard to imagine that. If you're in a tough spot, you're lonely, it's a friendly voice that'll talk to you. And disinformation and a lot of problems that can come up that we'll have to wrestle with. So it's not what's going to make the technology work better, but it's where does the technology fit in, and how do we all adapt to it and fit into it. And just yesterday was this, you might have heard of this open letter from a lot of prominent scientists saying, hey, this just got crazy. We need to take a pause. And so in this letter they're saying, we need to take a pause for at least 6 months and not train any more AI systems that are more powerful than GPT-4. So this was signed by a lot of prominent scientists who on kind of a lot of sides of this debate, saying like, hey, this got really weird really fast, and there are not sufficient guardrails in place. It's an interesting concern, absolutely, absolutely up for debate. And so I think at the same time, I don't want to end on such a somber note. I think our AI assistant friends are here. If you're not at the point where you're using ChatGPT to kind of like write the first draft of an email for you, you should be. Like, it'll get you 80 or 90% of the way there, and then you can go in and like tweak it and fix it. And I think that a lot of that stuff will make us faster and help us get better over time. So just summarizing what we talked about today, we talked about the history of generative AI, especially in text and sequences. We're going to see a lot of new modalities, a lot of new products here. And just to kind of anchor us in context, it was really only about 2012 were the first papers that this deep learning thing could actually work. Before that, deep learning was kind of mocked and kind of sneered at. So we've only been doing deep learning for about 10 years, and look where we are already. So it's going to be a really wild next couple years. So thank you so much for your attention. This was a lot of fun, and I don't think we have time for questions. Maybe one question.
Why don't we take one or two?
Yeah.
Can I grab that?
Yeah. All right, thanks a lot.
Okay, yeah. Let's take one or two questions. If we have questions, let's raise your hand.
I'm curious about the reinforcement learning part of this. Mm-hmm. So, and specifically the business end of that. Like, how did these small research teams get access to human labeling on the scale that they would have needed to cover all these different contexts, code generation and images and so forth?
Yeah, so they used it for. Actually, that's a good question. I don't know about the context part, but they use Mechanical Turk and things like that. And there's a couple companies that specialize in data annotation and data labeling, and there were a couple of them that got very quickly pivoted into supporting this for OpenAI. One was called Surge, and one was called Scale. And so they just open up armies of humans, like to the order of like thousands to tens of thousands, and you just kind of pay them by the I don't know what, and you can generate lots and lots of samples and feedback like that.
Anyone else have a question? Yeah, okay, right here, perfect.
Given this current state of things, what we do and don't know, there's a lot of fuzzy questions out there. What's like the thing that gives you the most hope and optimism versus what gives you the most concern? Like I saw a couple of weeks ago with someone, they put the AI online and it paid someone to get around CAPTCHAs, and
yeah,
is this how it starts? But what do you think?
I think the optimism is, I can say vaguely, there's a lot of people working on doing the right thing. And I'll have to say that vaguely, but it's not going on lightly in terms of guardrails, in terms of battle testing this stuff, in terms of kind of poking and finding holes. There's just as much energy going into that as there is in kind of being amazed at how quickly it's changing. And so, and again, I don't think kind of coming to the question of kind of replacing jobs and things like that. I mean, it's a transformative technology, right? Like, we have to acknowledge that, and we were all alive to see it. I think we're going to change the way we work. We're going to change our jobs in a big way. There's going to be a lot of things that our AI assistants are going to help us do faster. That's going to allow us to think about different things.
One last one. Anyone? All right, over there. Run over. Sorry, pardon me. Come through.
I'm curious about this call to put a pause on training, which I had just read about last night. I'm curious if you think there's any anti-competitive motivation for people signing that letter?
It's an interesting question. I actually looked through all the signees last night. Most of them are academics. Very few people at the tech companies seem to be willing to put their name on the list. I don't know if it's competitive in the economic and capitalist sense. I think it's genuine scientific and social concern. But then at the same time, it's, that's what's driving the arms race. It's capitalist intent between these big companies. And at the same time, you call for a pause and think about, if we pause, what are America's adversaries going to do? You can't ignore this from a national security lens. We could pause, but others are not. And so, as with any arms race, it's a very tight and tough situation. This time it's driven more by I would say capitalist concern than otherwise, but yeah.
Great. All right, let's give Keegan a big hand for that awesome talk.